time. We actually want you to. Okay, so what I thought I would do is maybe repeat what Dave was doing. I hope that's okay. At the end of the last lecture, I just got a little bit lost in the notation, and so I thought I would kind of sum up in my own way, but sum up what Dave was saying about continuous time. And so let me remind you of the setup here. I hope you can everybody see my screen here, my notebook over here?
Yeah. Can you make it bigger?
Sorry,
hide the header.
Like that, and like that.
Sure.
Is that good?
Yeah.
I've got like lots of screens that you can't see, like the chat and the panelists. I want to keep an eye on it, but it's also incredibly distracting. Okay. Anyway, this is a copy of.
I can keep an eye on that. Yeah.
Okay, you can keep an eye, then I can get out of my way. That'd be great. Okay, so let me go ahead and start. This was the notebook that Dave, you were doing on Monday.
Mm-hmm.
Here's kind of like the end of the story where we found out that we can more or less find a continuous fit to this discrete data. And maybe I can also just sort of set the scene here, which is, maybe I'll do it like you would do this. Let me remind ourselves the story. I think everybody knows this, but it's probably more for me than everybody else. But at every time step, I'm going to just type this. At every time step, there is a probability P of recovering from the infection, right? Or recovering from something. Infection, or 1 minus P of remaining infected, right? So this is sort of the basic story. Right, so that's kind of the basic story, and we were plotting the cum sum. So we were plotting the cum sum, which is the probability of being infected at from what is it? It's the probability of being infected from time 1 to n. Wait, let me say this right. I'm not saying it right.
Well, it's the probability that you got infected at some point, at some time between 1 and n, I'd say.
Wait, what are we assuming that we're starting infected or non-infected? Let me get this story. See,
recovering. The probability of recovering, sorry.
From the infection, right? So this is the probability of recovering sometime
between 1 and n.
Between 1 and n.
Inclusive. And we should just remind people that cum sum means cumulative sum.
Cum sum, which is an abbreviation for cumulative sum, right? Which is, so if you have a vector, you take the initial string and add them up. As in, well, why don't we just remind people what it is, right? So if you go cum sum of 2579 is, do I have to make the commas?
Yeah.
Cum sum of 2579 is 2 plus 5 is 7, 7 and 7 is 14, 14 9 is 23. Right, so we're plotting the cumulative sum. So I basically heard you talking about doing an analytic sum like you might do in high school. But of course, there's a very simple way to, just a kind of way of thinking about it, which is that that if you look at 1 minus this thing, right, that's the probability of not recovering any time between 1 and n. That is failing to recover.
That's a good way of thinking about it, yeah.
Failing to recover each time from 1 to n, and these are independent. So this is simply 1 minus p for each time, which is 1 minus p to the n. Done.
Nice.
Right, so you don't need to remember sums of geometric progressions to get this answer. Right, so the cum sum, therefore, is equal to, which is exactly what you said, Dave, 1 minus p to the n. Right, that's the very thing you were plotting if you go back to the top of your thing.
And it's a good opportunity to remember how to do sums of geometric progression anyway.
Yeah, I guess it never hurts because everybody always forgets it, I think.
And, you probably wondered in high school why you cared about the sum of a geometric progression, and now you know why, because it tells you
This is one reason you would.
One way of
Yeah,
calculating the thing. Yeah.
I suppose that's true. I actually think lots of MIT students remember this sort of thing because MIT students are very clever. Though MIT students are also human, and if you don't use it, you might forget it. You might even forget you ever learned it. I don't know.
Yeah.
But probably not MIT students. Okay, so that's just one thing I wanted to point out. Then I also think, I'm not sure if I'm saying this right, but I feel like there were two sort of continuous facts that are kind of connected, kind of interrelated, but in my mind, they're also distinct and worth at least teasing apart. And I just wanted to somehow do that. And one is that now that we've got this answer, 1 minus p to the n, 1 minus, fact one is that it's possible to interpolate, right? And if we, obviously, you proved it on Monday, Dave, that you can interpolate it because look at how nicely this green curve kind of interpolates. That is, it fills in all, it fills in through continuous time all these discrete steps. I mean, it couldn't be prettier.
Passes through all the points. Yeah.
It passes through all the points. There's another fact, which is that you can go to a limited, if you think of P as sort of a rate of recovery, it's possible to go to a limit if you kind of let time get smaller and smaller. And I feel these two facts are worth teasing apart, even though they are indeed closely related. So if you don't mind my just kind of pointing that out, I'd like to do that. So here, let's go ahead and take your numbers. P is 0.1, here's your lambda. And let me point out that, that here's the cum sum. I don't know why I'm calculating it again. I could probably get rid of it here. Let's just get rid of it. It's probably just in the way. Just to point out that here are the values, here are numerical values in the first column of these cumulative probabilities, right? So, by the way, if we took a different point, if we took 0.9, I think it's easier to actually look at the numbers. May I do that? Can I take the p equals 0.9 instead? Because then you can see the pattern much more easily. Or even, I don't know, maybe even 0.8, is that worth doing? No, I think 0.9 is a good one. 0.9 one, we could actually see the pattern much more easily. Yeah, let's do that. So here's everybody sees the pattern. The first column just basically shows you the cumulative probability for n equals 1, n equals 2, n equals 3, and so forth. Okay, and of course, you pick the lambda so that this just shows that you're interpolating, right? That if you replace 1 minus p to the n essentially with e to the minus lambda t, which of course, I mean, it's sort of easy to see that if you take this equation here, I mean, this is just simple exponents and logarithms and things. You're going to obviously get the same answer. I could go back to your 0.1, right? But I'd also like to point out that what's really going on here is nothing fancy. It's just the simple fact that let me do it this way. Let me go back to high school. In high school, everybody learned that 2 times 2 times 2 times 2 times 2, I'll do one more, is what? 3, 4. This thing is the same as 2 to the 6th, right? You learned about powers, right? You learned that you can write this as 2 to the 6th, okay? And then later on, you learned that you can take 2 to the 3.7 or whatever you like. And you learned that, of course, you're not multiplying 2 3.7 times. That has no meaning, right? That'd be silly, right? It's not like we're going 2 times 2 times 2 and, oh, and a little more 2, but, not quite the 4th 2, right? We're not doing that. And yet somehow we've got a perfectly good way of smoothing out the power function. And, you all know how that works. And you do it in such a way that 2 to the a times 2 to the b, is 2 to the a plus b, which of course makes sense when they're positive integers, but it also makes sense when they're not. And, you all learned that in 10th and 11th grade, and you don't need to hear it again from me, right? But that's what's going on. And so I'm going to point out that, for example, you could evaluate this probability because powers just work. Here it is at half times, right? 1, this is 1, 1.5, 2, 2.5, 3. You can, whether you write it using your 1 minus p to the n, or if you write it with the e to the minus lambda t, it actually doesn't matter. I mean, n sounds like an integer, but here I am making it, you know, a non-integer. It's a half, or, you know, I could step by a quarter as well. Obviously, the math doesn't care, because in the end, all I'm doing is I'm just making sure that 1 minus p to the n is e to the minus lambda t. So, you know, you just, and it's just a simple logarithm that makes that happen. So my point is, just to repeat, I know it's kind of obvious, but the fact that you can smooth out the probability is just a simple statement about smoothing out powers. Okay. Now, then there's,
yeah.
Anybody want to ask a question? Or is that just somebody's?
That was me saying, well, but it's, yeah.
You're not buying it? You want to argue?
No. I agree with you. I agree with you as far as that, as far as it goes. That's a good way of thinking about it. But then there's this issue about taking, you know, taking steps which are more steps in time, right?
Yep. That's the second.
Oh. Okay. I see.
Yeah, I'm just, like I said, I'm teasing apart 2 points just to make it simple.
Right.
I like simplicity, right? That's just me.
Yeah.
I'm too dumb to do complicated things. So if it's not simple, I just can't appreciate it. Okay, so, oh yeah, so I'm not sure everybody who came in late would have seen this little message. So I'll just put it up briefly again, that a couple of folks already been volunteered to both be seen and heard. You could do just one or the other, I guess. But if you'd like to, I have to make you, you know, either turn on your chat or make you a panelist. Turning on the chat turning on the allowed to talk, I guess. It's not the chat. I've got the power to do that, and I'd love to hear you or see you, but you have to agree to be recorded and seen. So if anybody wants to do that, just let us know in the chat or otherwise, and we'll make you that. Okay. Now the second point, which, I mean, I just kind of wrote it out here, but let me try to talk this through a little bit. So there's, if one thinks of P, a probability of recovery, as a rate, suppose you think of P as the probability that I'm going to recover in the next 24 hours. Okay, so that's like a rate. It's a probability of recovery per time, right? So the whole idea of a rate is that you should be able to scale it up to smaller times and larger times. And, you know, of course, the whole calculus thing is that it's, you know, you get a limit and all. But like, let's just think this through. If your probability of recovering is in 24 hours is P, there's a bit of a temptation to think of it as a rate and say, well, then in 12 hours, my probability should be maybe P over 2, or approximately P over 2, right? And in 6 hours, that's a quarter of a day, maybe my probability is P over 4. Or if I had a 1 hour, right, maybe what I should do is take I should take P over 24 is my probability for the 1 hour. Now, of course, if you do that, the probability of not recovering is 1 minus P over 24. And if you then go ahead and say, oh, we're going to work not by the day, but by the hour, then you're going to raise this to the 24th power. And of course, this is not going to equal 1 minus P anymore. Does this equal 1 minus P? The answer is, of course not, right? So this is not equal to 1 minus P because of the compounding that happens, right? It's the same story if you've ever looked at compound interest and stuff in high school and whatnot, that eventually, you know, as this number 24 gets bigger and bigger, that is, if you divide your day into smaller and smaller time intervals, then you're going to get something that's no longer 1 minus P, but you will get a limit, right? And so you'll get 1 minus P. So I'm going to replace this 1 over 24 with something small, and I'm going to use Dave's notation. I'm just going to call it delta. Right, and so I'm just going to call this 1 minus P delta. Delta is like 1 over 24. And so that would be raised to the 1 over delta, of course. And of course, this thing is no longer 1 minus P. It's probably not that far off from 1 minus P. But what does it equal to? And this is the sort of thing that, you know, you learn in calculus. And for some people, it's the very definition of the exponential. There's this, that maybe you've even learned it this way. Like maybe you learned, I don't know how you learned it in high school, but maybe you learned that if you had if you had $1 at 100% interest and you divide it up over n time periods, what would you get? And then the answer is, of course, E, right? That you get. So, for example, how does it work if you took, for example, you got $1.50 every 6 months, you would get, right? You get 2 1/4. If you did it quarterly, you get 2.44. Right here, Dave would probably tell me to, times per year, to not type this twice. So here
well, no,
we go.
I would just say just do an array comprehension.
I could do that. Okay.
1 over n to the n.
How about, can I do it in powers of 2?
You can. You don't have to.
I like splitting years into halves, quarters, and so forth. And of course, this is going to head towards E. Some people learn E this way. So what does E look like? Can I just type E anymore? I think not, right? But exp1 still works.
You can type \Euler.
\Euler. Oh, and it's even like it's a funky looking E as opposed to the regular E. Can you see the difference? And it even puts it out nicely. Yeah, so this is heading towards 2.718. We can go a little further. So this is getting there. It doesn't get there very fast, but it's getting there. So some of you may have actually seen that in high school too. And then there's the generalization of this thing where you could put in X here, like, you could put in 0.3, right? And that would be the same as X of, this would be this to the 0.3. Right, so this is, you can put any number here and then it's just the exponential of that. So back to the main story, this thing here, it's not equal to 1 minus p, but what it is equal to is the \Euler, thank you for telling me that, raised to the minus delta. So if you think of this as a value at time step t, then this is e to the minus delta t, and you can take 1, wait, am I going to get it all mixed up? 1 minus e to the minus,
should it be p instead of delta?
Yeah, 1 minus pt, exactly, thank you. It's e to the minus pt, and then if you want 1 minus will be the probability of recovery, and this becomes an honest to goodness probability distribution that is now continuous in time, right? So the way that one can say this in simple English, that, in fact, I'll write it out, that the probability of recovery somewhere from time 0 to time t is this value. This becomes a continuous probability now as opposed to a discrete probability. So there you have it, Dave. This is the way I like to think of it.
Very good.
It's not any different, really, from what you did. Maybe I'm just repeating it, but I thought it
right, but I think it's clarifying. Yeah,
it's always worth repeating. It's always worth hearing things a few ways.
Yeah, great.
All right, so that's this part. You were going to say more about the exponential,
Yeah,
Dave?
yeah.
And then I can do, depending on how much time is left, I can start off on differential equations. And again, now that I'm you can take over the screen and I can see if anybody else wants to be seen and heard. We would certainly love to see and hear you, but only if you're willing.
Okay, so as Alan was just saying, so what do we do? Last time and then just now we looked at this cumulative distribution function for these geometric random variables, and we showed that when we take these jumps smaller and smaller, something converges, right? So it's pretty subtle to work out exactly what it is that is converging. Well, so what is converging are these functions. Which functions? These distribution functions. So, so apparently mathematicians, so physicists call this the cumulative distribution function, but mathematicians realize that actually this is the thing that defines a probability distribution, and so they just call it the distribution function without the word cumulative, often. Okay, so that, what is that? Is this function.
I have to tell you that confused me for like 5 years.
Yes, it's all very confusing. The names people give to things are confusing. So, so what is that? It's just this, as Alan was saying, it's the probability that this thing, this whatever it is that we have, this object, this random variable, the thing with a random outcome, which is when did you recover, in this case, that is has a random outcome with a certain probability distribution. So a certain probability that it happened at each time, let's say. What is the probability that that's less than t? And what we've just discovered is that for an exponential random variable, we have this formula. For this limiting process, these things are converging, and they are converging to this function, right? So that's exactly what Alan was just showing, that we had this discrete cumulative distribution function, which, as I said, was trying to insist it has this weird staircase shape because it's discrete. And as we take the steps smaller and smaller, right? So then I'm going to do an intermediate one that looks like that. I get another staircase function. And as we take the steps smaller and smaller, this function is actually converging to a limiting function. And that limiting function is this. And so that is, in more advanced courses on probability, that is how you have to think about these things. You have some functions that are converging to other functions, and you have to understand, in what sense do they converge, and etc.
Don't get into that.
No, I'm not getting into that. No, I'm not getting into that. I'm just saying.
Well, I'm not telling you, Dave. I'm telling the students not to get into that.
Oh, right. We have some functions converging to other functions, and so that is a tricky thing to talk about. That's all I'm saying. So then that's why measure theory is so hard, basically. I think, sort of. So this isn't. So what is this called? It's called an exponential distribution. So this is the distribution function, the probability that my recovery happened before time t, and t can be any continuous number, as we've been trying to insist. So this is an exponential distribution with parameter lambda. Now, what is this fz of t again? It's just the probability, right, that my random variable, which I'm calling z, is less than t. We don't know what z is yet. So z is called an exponential random variable. So it's a continuous valued random variable. It's a random variable whose outcome is a continuous number t, a real number between zero and infinity. So continuous or continuous valued random variable. Okay, so if we think back to the discrete random variables, the geometric random variables, we could talk about the probability that we decayed at time n. And now, so far, all we've said is what's the probability that we decay before time t. So can we actually find the equivalent of a probability mass function? Remember that was the probability that my geometric random variable, which I was calling x, was equal to n. Right? Can we find the equivalent of that? Well, so if we have this probability that I'm less than or equal to t, now that I have a continuous thing, I have to replace my sum by an integral. And so this is going to be an integral over something. And that something I'm going to call little f of z. And that is called the probability density function. And so this word density is very important. And it took me a long time to understand why it was called this. And it's just because, what does that mean? It means that, well, the probability of being of decaying at a particular moment, right? At 3:01 p.m. with 27 seconds, 27.1279 seconds, the probability of decaying exactly at that moment is actually going to be 0. For any particular moment, the probability of decaying at that moment is 0 because there are a very large number of moments, right? An uncountable number of moments, moment in time. But what I can talk about is the probability that I'm in some little tiny interval of a length bigger than 0, dt, or delta t, let's call it. Right, so if delta t is 0.01, that's some small number, what's the probability that I'm in the time that I decayed within the time interval from 3 until 3.01? I can talk about that number, and it's approximately given by this product, fz of t times delta t. And when delta t goes to 0, that gets a better description of that number. And so what does it mean to be a density? It means that this thing has units 1 over length. Right? I need to multiply it by a length to get the probability of the length of the interval that I'm in. And that's why it's called a density. Okay, so what does that look like from my exponential distribution? Did I forget to write that down? I did. So what do we have to do? So what is the relationship between this cumulative distribution function? So for the exponent, so let me make a new slide. So for an exponential random variable, what do we have? We have that the probability, the distribution function, the cumulative one of my thing is 1 minus e to the minus lambda t. So that's the integral from 0 up to t of my f z of t dt. So what is the relationship? How do I extract this f z of t from this capital F z of t? So feel free to chat.
Don't use the same t. Don't use the same t in the dummy integral as you do for the limit.
Sorry. Yes.
Make it u or something as the dummy variable.
S. U, you like u? Okay. F t f z of little f z of u du. Thanks. Yeah, that's a cardinal sin to do that.
Physicists do it all the time. Mathematicians hate it.
Okay, so how do I extract fz if I have if I have its integral? Answers in the chat. Everybody should know this.
Take the derivative.
Yeah. So by the fundamental theorem of calculus, I can just sort of differentiate both sides, and I get that little fz of t is the integral. The derivative d capital Fz by dt, well, let's not write it like that. The derivative f primed evaluated at the point t. So if fz of t is 1 minus e to the minus lambda t, then what is the derivative? Little fz of t. Can you distinguish when I'm writing capital F and when I'm writing little f?
That's fine. It's even better, but it was fine already.
What is the derivative of this function? Somebody say it or type it. Does everybody remember how to differentiate this function? If not, then we're in trouble.
It's hard to, it's not that hard to write. I guess it's a little hard to write.
So the 1 goes away, right? Derivative of 1 is, so it's a sum of two things, 1 minus, or difference of two things, 1 minus something. So the derivative is the derivative of 1 minus the derivative of something. So 0, and then I have to differentiate 0 minus the derivative, which you could write like this, derivative of e to the minus lambda t. So what is that going to be? It's the derivative of e to the something. That gives me e to the same thing. And then I have to differentiate the something, right? Chain rule to differentiate the something. And I get the something is minus lambda t. I'm differentiating that with respect to t. And that gives me just minus lambda. So it's times minus lambda. And so I get lambda e to the minus lambda t. Okay, so that is the probability density function, PDF, of the exponential distribution. And that is supposed to be, it's the probability that at time t you decay, except you have to remember that there's this dt around, right? So the probability that in some little interval near time t you decay is this number times the size of the interval, the width of the interval. Okay, so let's look at this in Julia. I'm going to stop sharing my screen again. then I'm gonna share my, it's so annoying, it really is. So unnatural to. So, 9.
I really do respect, Dave, that you go ahead and just start with an empty notebook.
I like doing that, yeah.
Yeah, I know. It takes a certain kind of confidence. You're good at it.
It takes just experience, basically.
It's kind of up there with, teaching, starting with a clean blackboard, right? Just an empty.
Right. No, I mean, it's very scary. No, it is very scary. I mean, I know a lot of people, students and researchers and whatever. If you start with a blank piece of paper, it's the worst. So, I always say, well, if you're starting the homework or whatever, you're given some information, right? You're given that maybe the initial value is 3. So just write that down and you immediately have a non-blank piece of paper, and then it's much easier. It's just psychology. Psychology is a weird thing, human psychology. So we've got okay, so we have a probability density function, so let's call that f of x, right? F of t, sorry, is exponential of minus, it's lambda times exponential of minus lambda t times t, right? You have to put the times in. Remember that. In Julia, you have to put the times in unless it's an explicit number that you're multiplying. Okay, and now I want to plot that function. So how do you do that in Julia? So we haven't really seen that. So if you just put plot f, where f is a function of one variable, it will try to plot that function in some sensible way.
Really?
So let's see what it does. Sorry?
It knows the interval?
Well, so let's see what it does. So it does not know the interval. Yeah, so the point is that this function, yeah. So you see, okay, it chose the interval -5 to 5. So by default, it chooses the interval -5 to 5, which for us is completely useless. So we do have to tell it.
If we really gave grades, which of course we're not doing this semester, I would this is the time where I would utter automatic A to someone who can get rid of that character ignore due to Unicode.
Don't really, yeah. So that seems to be that I want to have this should say 2 times 10 to the 4. I think that's the problem. I think this thing is not yeah. So there's. Yeah, apparently, and I did ask somebody about this, and apparently they said that there's some reason why Unicode is not Unicode. So Unicode is this extension of fonts where you can have all these weird characters, and apparently there's like times and superscripts, and apparently there's some reason why Unicode is not enabled by default for this plotting package which we're using, which is called GR, and GKS is like the plotting interface or something. And so that's what's happening, I think. So there should be 2 times 10 to the 4, 2 dot, or I don't know what, they're using some symbol, and for some reason something's going wrong with that symbol. Okay, so sorry about that. So that's a new thing since.
I still would say I'd give an A to anyone who could fix it, if I could.
Yeah, so you can do this plot F, but it doesn't do the right thing. So we'll actually have to tell it where we want to plot. So we'll just do something like from 0. So there are different ways you could do this, and I always forget. I think it's 0. Is it just 0, 5, f? No. Or is it f, 0, 5? Yeah. So you can just do plot f0, 5, but that's a different syntax than everything else we've been using in the whole course. So another way of doing it is just plot 0 from 0 with step sizes of 0.01 to 5. Plot the function f. So yeah, so notice that really I am giving it the name of this function, and it is, so what is it doing? It's automatically calculating f at each point in this interval, right? At each point in this range. So if I can actually see that by adding markers, and I can see what it's doing. It's, well, okay, so it's not doing what I just said. Oh, maybe it is, So let's yes, if we do 0.1 instead, we can see that it is actually doing that, yeah. So it's just taking this range and evaluating f at each point in that range. So how could I write that? I could actually write that as, right, R is going to be my range, my range object. And now I'm going to plot, I'm going to use that range object as my x coordinates, and the y coordinates are going to be what? Yeah, so all through the course, we've been having a vector of x's and a vector of y's. Here, instead of a vector, I'm going to use a range, which is just, you know, a sort of implicit way of representing a vector with equal spacing. And then what am I going to do for my y coordinates? I want to evaluate this function at each point. How could I do that? Put answers in the chat or by voice.
You the dot evaluate r.
F dot of r, right? That's going to apply f to every element of my range.
What did you say? That if you don't apply it, it doesn't work?
Don't apply it, meaning what?
If you just, I mean, if you just did f as the argument.
No, it does work.
Oh, it does work. I see.
Yeah, it does work. I'm just saying that what is Julia doing under the hood? It's just doing that.
Oh, okay, sure.
So it's saying if I pass in a function, then what it's doing is automatically evaluating it at some set at this set of points. And if I don't even give it some points, then it will try and automatically determine some reasonable places to evaluate the function. Okay.
By the way, there are at least 2 data points that say that on Windows you don't get that freaky Unicode error. So it seems to be maybe a Mac or.
Okay, good to know. Yeah, it also might depend on which version of plots, the plots library you have installed. Okay, anyway, so yeah, so this is what the PDF looks like, right? So we don't really want the dots, right? Because, so this is, you know, an important thing that I keep saying, but, you know, looking at some of the homeworks, it's important to keep saying this. When we have discrete data, that is data that is only at certain points, we should literally draw it with points to say, you know, to indicate to the user, this is all, you know, this is the only information I know. But now we've reached the moment where I have real continuous functions that exist at every possible, you know, value of t. So then I don't actually want to plot dots, right? The dots were only to see what Julia was actually doing. Now I really want to plot the curve without dots and to say this is a continuous function. So that's what it looks like. And, you know, maybe we want to just make it a bit thicker, line width equals 3, and I'll have a bit of a stronger line. So that is what, you know, my PDF looks like. I could use an interact to change this rate lambda, right? So lambda is a rate. What is this lambda? It's the rate at which, you know, the decay rate, basically, the rate at which I'm recovering. So as Alan was saying, what is a rate? It's a probability per unit time. You can think of it like that. So in a little time delta t, the probability to decay is lambda times delta t. That's right? You know, I think that's right, yeah. So the probability...
Dave, can I draw on the screen just out of curiosity? Does this work? I'm going to try something. Well, if I go like that, does that draw like am I like circling the Y1?
Yeah.
Oh, that really works. I see. So can I? So this is time t, right? And this is the probability density.
Yeah.
Is that right?
Thanks. Yeah.
So if I were to, let me see if I could. Am I allowed to change colors? Or yeah, I can change colors. So that's cool. So if I were to like draw something like this, an area between 1 and 2, what would that mean?
What?
Can you see it? If I draw this area, am I drawing what I think I'm drawing?
Yeah.
Oh, no, don't move it. Don't.
Oh, sorry. I just wanted to draw it in Julia instead.
Oh, do you want me to erase?
No, it's fine. Because I'm going to have to remember how to do it. Yeah, I don't know how to do that.
How to draw it in Julia. I mean, I know how to draw the lines, but I wouldn't know how to draw the shaded area. Oh, fill? Oh, that's cool. Oh, that you got something filled above the curve.
No, yeah. I don't remember how to do it. There is some way of doing it.
I think you were
areas, yeah. Sorry?
You probably have to. Is there a fill below? If you did what you said before, or is there an option, you know, to fill below?
No, I don't remember. Can somebody look it up?
All right. Well, you can then go back and use my scribbling. That works. Well, you know, maybe one of our panelists.
So what do you want to ask people how you would calculate that area or what it means?
Well, I was first going to ask what's the interpretation of the area.
Yeah, got a good question. Yeah.
So actually, maybe I'll even start with a simpler question. May I start with a simpler question?
Sure.
Which is what is this entire area that goes out to infinity here and includes the orangey area as well?
Yeah. Good
What is the entire area under the curve? That shouldn't require too much thinking. What would it be?
1, yes.
Good, right? That's just sort of, the possibility of everything. And then what's the orange area, the part that's between 1 and 2?
What's the interpretation, you mean?
Yeah, what's the interpretation?
Probability they decay somewhere in between there.
Sorry?
The probability that you decay sometime between times 1 and 2.
Right. Exactly, decay, or you recover between, sometime between 1 and 2. Exactly right.
Great.
Did anyone figure out how to do the fill below? I can try to look it up. Do you want me to erase this? I guess you can erase it too.
There's an answer from Dan.
Oh, there is? Oh. Why don't I see the answer from Dan?
But I don't know, is that LU? Is that going to work? No, I don't know. Anyway, there's some way of doing it that I forget. Yeah. Okay. So now, this is all great, except, so now what do we want to do in our simulation? Thinking back to our simulations of random, agents moving around and whatever, these agents are going to recover. And before we were doing that with this geometric random variable. Now, what happens if we would like to allow them to recover at any moment? Right, so what we want to say is, okay, so before what we were doing in problem set 2 is to say, okay, we're just going to throw flip a coin with probability P, a biased coin, and wait until that comes up heads. And that will give us the value of our geometric random variable, which is how long we wait until we choose to recover, or until we happen to recover. But now, alternatively, what we did was had this clever method where we just generated that once and for all. And so now what we want to do is actually generate. So what would we like to do? We would like to generate a random outcome, right? So what is this plotting? It's telling me that the probability that I decay at near time 0.8 is given by the density 0.6. The probability that I decay near time 3 is given by the density 0.01 or something, given by this formula lambda e to the minus lambda t. But now what happens if I actually want to generate a random real number between 0 and infinity with this correct probability? Right? That's a different question. How would I go about doing that? So how to generate numerically what's called an exponential random variate rather than random variable. So random variate is just like the outcome of a sort of random experiment, such that when we do a lot of random experiments, we should get the correct density function. We should get the correct probability, for example, the probability that Alan shaded in between 1 and 2, the probability that my thing that I'm going to generate numerically lies between 1 and 2 should be the correct thing, which is the integral, the area under the curve between 1 and 2. In other words, the integral from 1 to 2 of the probability density function. That is what we would want to do. How on earth are we going to do that? So all that we have available in Julia or in any language, usually the base thing that we have available is some function like rand that generates a random variates with a uniform distribution in the interval from 0 to 1. That's all we have. And now we want to convert that into, I'll just make that a bit bigger. We want to convert that into somehow into this non-uniform distribution. Does anybody have any suggestions about how, what kind of method we might use to do that? how can we get a non-uniform distribution? Just any non-uniform distribution, not even this particular one. What might we choose to do? So we're allowed to use these uniform random variables, random variates, and we have to do something to them to get something that's going to be non-uniform. In other words, that when we've done this something to them, the probability that the new something will be in some interval is not going to be the same as all the other intervals of the same size. That's what uniform means, right? That probability. Right? So the uniform distribution is a continuous probability distribution as well, right? It has a very simple PDF. So I could say uniform PDF of X. What's the formula for that going to be? That's going to be the probability that I sort of fall at X. In other words, that I fall in a particular interval between, fall in a particular interval. What is the expression going to be for that probability density function of a uniform random variable, of this thing that rand gives me? What's the formula going to be? Was the question clear? Can we have answers on the chat or? So we might actually want to make that into a proper function. Oh, okay, we've got an answer for how to fill.
I'm not 100% sure it won't go above, but I think it will be fine.
Yeah, nice. Yeah, great. Thanks.
That's better than my scribbling.
Yeah, it is. So what's
But
going
I
on?
noticed that somebody else had asked, and so Dave Sanders on Stack Overflow, and Dave Sanders gave a pointer to a response.
Nice. I have to meet that guy.
He knows everything.
So so this is something new as well that you're going to need on the problem set 5. This is what's called an anonymous function. In other words, a function with no name, right? So although we gave it a name here, when we created the function, it had no name. And this is literally, it looks like an arrow, but it's literally minus followed by greater than, right? So I literally type minus and then greater than, and then it looks like an arrow. And so this is, so what is this? This is the function which sends, which maps t to x to the minus t. So in mathematics, you would write t maps /maps to tab, and that gives you this nice arrow with a bar, x to the minus t. And that again means the function which maps each value t, it maps it to x to the minus t. That it defines a function.
But could you use maps to in Julia instead of dash greater? Does it work?
If you look on the Julia issues, you'll find that I raised exactly that question a few years ago, and it was shot down in flames, which was very unfortunate. Yes, it would be very nice to be able to use this.
It would look pretty, yeah.
I don't really see why they didn't allow that. Anyway, so yeah, and then this fill true, we're just, yeah, so fill equals true will plot. So that here we're just doing a second plot where we say which region we want to plot between and fill that in. Yeah, thanks, Dan. And then the alpha is for transparency, just so that it looks less, full on. If I do 0.2, I get sort of this nice shaded region.
Do you have any idea how to make it gray? Like I guess the black with alpha equals 0.2 might be gray.
Color equals gray.
Or maybe black.
You need a comma.
Oh, yeah. I think I like the gray. Just anyway, that's me.
Oh, I don't.
All right. Well, you can go back to the orangey thing.
Okay. So great. Yeah. You can do all kinds of nice things in plots if you know how, and it's difficult to find out how. Okay.
You could do like color equals 3.
How are we going to do this uniform PDF, by the way? Can we get that? Anybody? Nobody. Okay. So it's just, you have the same probability wherever you are but only between 0 and 1, right? So if 0 is less than or equal to, so I can write that as \LE using the LaTeX abbreviation for less than or equal to, and then tab, and I get this nice less than or equal to symbol, or I can write less than equal to like this, as two separate symbols, but they both work. But this one looks nicer. 0 less than or equal to x less than or equal to 1. I can write that in one, double comparison. Then I'm going to give you 1.0, else I'm going to give you 0. And so then if I plot uniform PDF, and I do that between -2 and 2, we'll see what that PDF looks like. It looks like that, right? So 0 everywhere. There's no probability to be in those regions. And then the probability to be anywhere in the interval from 0 to 1 is the same height. And in order for the area underneath to be 1, we need the height to be also 1.
I wish it looked like a square.
It's like, sorry?
I wish it looked like a square. Can we make the aspect ratio 1?
Ratio equals 1. And then it looks like a square.
That looks like a square.
Yes.
That makes me happy.
And of course, we could do a uniform PDF between some other places, right? So suppose we want something that's uniform between A and B. How would we do that? Nobody knows. So
When I break it into two parts, there's that. And
between A and B, so outside A and B, it's definitely 0. What is it between A and B?
so what's the key fact? That the area has to be 43? No, that wasn't it.
42.
42 is the answer.
To life, the universe, and everything.
There we go. Jeremiah's got
1 over B minus A. Thanks. Yeah, 1 over B minus A gives me the right thing. So plot. So now I have a problem because I have to plot a thing which this thing is supposed to be a function that takes 1 argument, and I have a function which now takes 3 arguments. Oh dear. So what can I do? How can I turn my function that takes 3 arguments into a function that takes 1 argument? Hint: we just learned how to do that. Oh, we just learned that we can turn to our advantage to do this. So we can use this and anonymous function. So we're going to write the function that sends x to the thing I get when I send that x into uniform PDF with the A and B that I want, right? So let's say A is, I don't know, -0.5 and B is 1.5. Then I get uniform PDF from A to B, right? And it's going to plot this thing, and it goes from -0.5 to 1.5, and it has the height 0.5, and that will give me area 1 because the width is from here to here is 2. Great. So that's how we can do different uniform distributions. Okay, and so we need to know how can we actually generate. So if we have rand, by the way, how can we actually generate a random number between -0.5 and 1.5 with the correct probability? So with uniform probability, how could we do that? So let's call that uniform. So I'm going to have a function called uniform from A to B, which is going to generate a random variate which has a uniform distribution on the interval AB. Yeah, so somebody has replied that I could do 2 times rand minus 0.5. So if I do 2 times rand minus 0, so if I do 2 times rand, what's that going to do? That's going to give me, take a random number between 0 and 1 and multiply it by 2. So sometimes it'll come out small. Sometimes, so if I do Control Enter, I can rerun the cell again and again. Sometimes it'll come out as sometimes it'll come out bigger than 1, right? Because rand can give me a number bigger than 0.5. So 2 times rand can give me a number bigger than 1. And so if I take all of those numbers, so I can do that, 2 times rand of So let's say 2 dot times rand of 1,000. I'm going to take 1,000 of those numbers and I'm just going to scatter them. And so you can see that they go, the height, the value that I'm getting out of this operation, again, the x-axis is just which number, right? Which number n, which step n of my random number generation it happened on, and the height is which value actually came out. You can see that, yeah, it goes between 0 and 2, and they don't seem to be clustering in any particular way. They seem kind of uniform. So we'll see in a minute how to check that more carefully. So maybe somebody can suggest how to do that. In general, can we use our PDF to give a weight to each possible outcome when we use RAP? Yes, that's the idea. That's the question. How can we do that? That's what we want to do, right? This PDF, the exponential PDF, is giving a weight, a different weight, right? It's more probable that I get 1, something near 1, than something near 4. More probable, even more probable I get something near 0 than something near 1. So yeah, I'm trying to find a way to give more probability to those things. So far, with these uniform things, with this rand, I'm just spreading the probability out over a bigger interval, but in a uniform way. So if I do 2 times rand, I get something between 0 and 2. If I do 2 times rand, and then I subtract 1 from each of those, then I get something between -1 and 1. So that's now a uniform thing between -1 and 1. And so that's the answer. So uniform AB is A plus rand times B minus A. That will give something that's uniform between A and B. So if I do uniform of -0.5 and 1.5 for I in 1 to 1,000 as an array comprehension, and I scatter that, and that will give me something that's uniform between -0.5 and 1.5. Right? Great. So how could I actually check how uniform that would be? So can I actually look at the PDF? So this, this is giving me some data. Can I somehow get a PDF, a probability density function, from this data? Do we know a way to do that? So by which I mean, do you know a way to do that? Because we haven't discussed that yet in the class. What we've discussed in the class is, how can I do that if I have discrete data? You wrote a function called counts in problem set 2 that does exactly that. Or you can use count map from statspace. How can I do that for continuous data? What's that called? The same thing, but for continuous data. So it's going to tell me sort of how many points fell in each part of the interval. What is that called? A histogram, yeah. So if I call this date, if I just get this and call it data, and I'm going to type, okay, I don't want to see the output. I'm going to type histogram of data. This is a function in the plots.jl library called histogram, and it will automatically create a histogram for me. So a histogram is just like a bar chart, except that the width of the bars does not have to be the same. And these bars are now telling me how many things fell in this whole interval, right? Because these points are scattered around, right? So actually, let's draw the points as well. I probably have too much data. Let's reduce the amount of data. I can change the number of bins, by the way, like this, n bins equals 20. Right, so that's how the data fell. So that's saying that there's only 1 point that lies in this little interval, and there's 3 points in this little interval. So let's actually draw the data as well. So scatter, data, and zeros. So I can actually write 0 dot of data for the y-axis. That will apply the 0 function to each point in this data set. The 0 function just returns the value 0 with the same type. So if I do that, I can see where the points fell. And indeed, there was only 1 in this little interval, and there's 3, there's 2 in this interval, and there's 3. It's actually working. So let's put the point size, marker size smaller. Marker size 1, that's too small. Marker size 3, I never know what the default marker size is. Marker size 2, that's probably good. Yeah, hopefully you can see that. So you can just, go along and count by hand. Oh yeah, here there are 1, 2, 3, 4, 5, 6. And okay, so there are some on top of each other. So I probably want alpha equals 0.3 or something. And maybe you can see better how many there are. Here there's 1, 2, 3, 4, and it's at height 4. right? So that's what a histogram is doing. So it's summarizing the data by sort of removing some of the information, right? I'm actually losing information about exactly where the points are, but I'm gaining a sort of more I'm gaining a more global view of what the shape of the data looks like. Now, I claimed that this data was uniform. It's supposed to have the same probability to occur anywhere in the interval. And yet, if you look at this picture, you don't see something uniform, right? You see this massive gap here where there's hardly any data. And then there's this peak here where there's a lot of data, right? There's a lot of data clustered in this interval. There's not much over here. So this doesn't look very uniform, but actually that is how uniform data looks. So humans are very bad at looking at data, the way data is distributed, and deciding if it's truly random, in other words, truly uniformly distributed or not. But all of this is basically is because there's so little data. If I have more data, so let's just copy this and make more data. What's going to happen? If I put 1,000, then I get something like that, and we see that, oh yeah, well, it's not so wonky anymore. There's still, some places where there's a lot of data and some places where there's less, but it's looking more uniform. And if I increase that to 10,000 or 100,000, takes a little while. It's taking a while to actually calculate the histogram, and then scattering all of those data points is a terrible idea. So let's remove that scatter. That's actually what's taking the time probably, yeah. And now you see it, oh yeah, now that really starts to look a lot more uniform, right? So as you take a lot more data, if you have bins that are sort of the same width, you can show that the probability of sort of the deviation, so basically each of these, yeah, you can actually sort of study the distribution of how many points fall in each bin, and you can show that it's, there's a, it's like a normal distribution, it's a binomial distribution actually, whatever. And you can show that as you take more and more data, you expect to have basically, the fluctuations away from each of them being the same height are smaller and smaller.
Somehow I'm reminded of the fact that when I was a kid in the newspaper, this was, I think, the New York Post, they would publish the numbers, the frequency, like the lottery, the frequency of each number showing up in the lottery, and
right,
people would study these things as if it had a meaning,
and hope that they were non-uniform, that they could predict something.
But may I make a suggestion, even when you only had maybe 100 data points?
Sure.
So can you grab a data that's set that's smaller? So can you plot, rather than plotting that, can you plot the sort of data against 1 through 100 over 100? So the X argument is the sort of data.
Yeah.
And then the right argument is just, what would it be? 0.01 colon 0.01 colon 1. There's some magic numbers for you. 0.01 colon 0.01 colon 1. There we go. So I would say if that looked like if that looked like a straight line-ish,
yeah,
then you can say that the data is uniform.
Yeah, so what we've just plotted is a kind of cumulative distribution function.
It's not even kind of, it's actually, sometimes it's called a percentile, but it really is just a cumulative distribution function.
The cumulative distribution function of the empirical data set that we just produced, the sort of just the data. So it's called the empirical cumulative distribution function.
I'm a big believer that humans can see this as, tending towards a straight line a lot more than seeing the histogram as being
You're probably right.
Flat.
Yeah, so if I say data equals this, and we plot this with ratio equals 1, I'm not going to use ratio equals 1. Oh yeah, we are.
If you want to remove the magic numbers, you could change the 100 to an n, and then put like 1 over n where you have 0.01. You see what I'm saying? If you make your first line n equals 100, above the data equals.
Yeah.
If you go n equals 100,
right?
Or 1,000 if you want to move to that, right? And then this is n, and then that's 1 over n. 1 over n, 1 over n, 1. There you go. Nice. Then you can see what happens when you add more data.
And then we can plot a straight line between this point and that point and see how far away we are.
You can certainly do that. Yeah, you
That's
could go plot minus 0.5, 1.5, 0, 1. You could certainly
do
do
that
that.
again. Sorry.
Plot the x is minus 1, minus, what is it? Minus 1.5 and 0.5, right? No, don't do all that. No. Could I just see the x-axis? Scroll up slightly. Just do minus 0.5 and 1.5 at comma 1.5. No.
Oh, come on.
Just do in square. Yeah, just do exactly as I say. Okay. Delete everything in the parentheses.
Oh my goodness. 0.5. There we go. Something like that. Delete everything in parentheses. Yeah, go ahead.
Okay. All right, just delete.
Yeah.
There you go. Left bracket. Minus 1.5. That's a square bracket. Minus 1.5, comma 0.5. Okay, then outside the bracket, comma. Left square bracket, 0, comma 1.
Oh, I see. Well, that's.
Oops, did I? Oh, sorry, it was minus 0.5.
Okay.
Minus 0.5 to 1.5, whatever the intervals are. Sorry, it was instead of minus 1.5, it's minus 0.5, and the right end is.
Okay, good. Thanks. Yeah, I mean that's okay, except I actually want a function, right? I want to know it's the same sort of idea as before. Right? I have my cumulative distribution function describing my data, and I have the cumulative distribution function describing the true uniform distribution, and I want to know how far away is this function from that function.
Yeah.
There's actually a statistical test called the Kolmogorov-Smirnov test. Kolmogorov-Smirnov test, which exactly tells you, is this distribution function close to this distribution function?
I've never been a big believer of that KS test, but everybody swears by it. By the way, why don't you try changing 100 to 1,000 or 10,000 just for fun?
Yeah, so it gets closer, and then I do 10,000, it gets even closer, and etc. It gets very, very close. Yeah, great, nice. Okay, cool. So we've just proved sort of numerically that as we take more and more data, the distribution function will converge to the distribution function of the uniform distribution. Great. Okay, now let's do non-uniform distributions. How am I going to generate a non-uniform distribution? So I start off with my RAND. I'm going to do something to RAND. What can I do? There's not much, there's not many options. There are many, many options, but they all have the same kind of idea. Can anybody think what I could do? So far, what have we done? We've just added something to RAND and we multiplied it by something. What else could I do? So we sort of transformed RAND, right? Transformed the result of RAND. Apply a nonlinear function, yeah. So what's your favorite nonlinear function? So maybe x squared. So let's try that. So if I have, x goes to x squared, that function takes any x to x squared. I'm going to apply it to a load of random numbers. So let's say I have 1,000 of them. I'm going to apply it, and I'm going to call the result data. So that's not necessarily the best way of writing that, but that's a way of writing it, right? And I get some numbers, and of course, I'm human, so I can't, look at those numbers and see what's going on. So I'm going to, as usual, plot them. So let's just go ahead and do the standard thing, just scatter them just like that. What do we see? Just by eye, what do you see? Hopefully you see that it does definitely look different than it did before. What's going on? Well, they're kind of crowding around down here, right? And there are less of them up here. And so if we now look at the histogram of the data, that'll tell us how many are down here and how many are up here, right? That's what the histogram does. It's sort of projecting, it's sort of shining a light, shining a light from over here, a horizontal light beam, and basically you have a darker shadow when you have more particles. The height of the histogram is how dark the shadow is, right? Or that's one way of thinking about it. Maybe, yeah. So let's do that, and then we get that. So we need more bins. M bins is 30. something like that. Okay, that's not very convincing. So let's take more data. Don't be afraid to take big amounts of data. I mean, you have to build up bit by bit. If I put 1 billion in here, then it's going to take too long. So, okay, something like that. So now we've got a lot of data, so we can have a lot of bins, and we start to see, what do we start to see? We start to see a very nice non-linear result, non-uniform, non-flat, right? So let's take 1,000 bins, and you see that. So what is this that we're drawing? We're drawing the empirical probability density function, actually, right? So, so I can actually, can I remember how to do that? Is it that? No. Hist style. There's some way of, because what it's doing is drawing boxes, right? So it's confusing because it's, I don't remember how to do that. I just want to not, it's drawing boxes, so it's filling in this whole thing. But really what it's drawing is a curve. And this curve is a non-uniform probability distribution, right? So I can actually make it a density by doing normed equals true as an option to this histogram function. And now this will give me something of area 1. So that is a probability density function. Okay, so finally, how do I get an exponential distribution? So it turns out that whatever function you apply will give you a different distribution, and you can actually calculate in some cases what that distribution will give you. And you can also go backwards and say, if I want to get this distribution with this density function out, how do I do it? And the answer is you calculate so as you see in a probability class, you calculate the cumulative distribution function. So we know what that is for the exponential distribution is 1 minus x minus lambda x. So that's what we're going to call sort of capital F of x, lambda times that. And now we actually want to invert that function, it turns out. And so, you set y, mathematically you would set y equals capital F of x, and then you want to solve for x in terms of y. So you can do that and you get the following. Y is, so if x is rand, then y, the inverse of that is the inverse of the function that you need to take the inverse of. It turns out to be y equals minus 1 over lambda. Well, you can write it as just minus log of x divided by lambda. And so if lambda is 2, say, then I do that. And so if I have a load of data given by a load of uniform random samples, let's call those x's, and I have this magic transformation function. Transformation of x is minus log of, and it has this lambda inside, minus log of x over lambda. Then what I want to do is apply transformation element by element to my x's. So I'm going to do transformation dot of x's. And this syntax actually works if I then put some value of lambda, for example. So here's my lambda, 2.0, put lambda in here. That will actually work, just like that. And so it'll keep the same value of lambda for each x, and it'll take each x in this array, and it'll give me a new array where I applied this function to each element of the array with this constant value of lambda. So it's step hist, apparently. Step hist equals false, or what? What do I write?
No, replace the word histogram in the front with step list.
Really?
I think so. Try it.
Oh, weird. Okay, thanks. Yeah, that's what I was trying to do. So that's some kind of probability density, right? Probability density of some distribution that I don't even know what that name of that distribution is. Do you know, Alan?
What is it? What is it? Oh,
actually, so this actually has a singularity that goes off to infinity up here, like a square root, right? Because it's the inverse of this function.
Yeah, you have to invert the function and take the derivative or something, right? So probably like 1 over the square root of x, maybe, I don't know.
Oh, maybe it's even
1/2 of the square root of x.
Or maybe it's even cubic, the singularity. Anyway, yeah.
No, I actually think it's 1 over 2 square root of x. You want to try it?
1 over 2 square root of x.
Maybe. That's just a guess. That could be wrong. Try it. You need a dot, or you need a. What are you doing? Oh, okay.
Looks
Am I
good.
right on the money?
Yeah.
There you go.
Cool. So it is the distribution with this probability density function. So I don't know. Do you know what the name of that is?
Doesn't have a name. It's not worthy of a name.
So yeah.
Probably it's the
So
Sanders.
let's finish this off. So I've got my data. I just got it by transforming these things, and now I'm going to histogram it. Well, first of all, we'll scatter it. I just applied this other sort of I was going to say random, this other arbitrary nonlinear function, right? I just guessed it. I just picked it out of a hat, and I get this. You can see that that's really clustering downstairs, right? Really sort of, there's a lot down here and very little up here. And if I do a histogram of the data, and I add more bins, I see something like a lot more bins. I see something like that. And if I add more data again, oh, come on. I see this nice curve. Let's have some more bins. I see this pretty nice curve. And if I put y scale equals log, I think this is supposed to be an exponential distribution. So it's supposed to have some kind of exponential tail, exponential behavior. So I put a log scale on the y-axis and I see a beautiful straight line. And indeed, this is an exponential.
Can you do his steps and as well with the y scale? Does that actually work?
Do what, sorry?
His steps.
Oh, step hist.
Step his, whatever. Yeah.
Yeah, great.
So that looks a little better.
Yeah, beautiful.
And
so, and
you want to explain why it kind of loses it at the end? I think that's sort of interesting.
So this was supposed to give me the exponential distribution with a particular PDF, right? So let's check that. So that was supposed to give me the function lambda, this same lambda, times x of minus lambda times x. And that did not work.
What's the x-axis? Can I see? Were you... Wait, why are you going from -5 to 5 in the original one? Or why... Wait, why is the new plot going from -5 to 5?
Because that's where the stupid thing chooses to put it. Oh, I didn't normalize the histogram. There we go.
That's better. Oh, that's pretty.
Thank goodness for that.
And
there we go. Yeah, so it is the correct PDF, right? So that is the nonlinear transformation that we need. And Alan asked to, said we should discuss this. What's going on here? So basically, each of these is some huge value, right? So we've got this is sort of the discreteness of the data that we saw in this scatter plot, right? There's only one value up here because I'm choosing, I don't have that much data. And however little data I have, right at the top, the sort of largest value will be very rare. And so I'll get this weird effect where I don't really have enough data to fill up my bins. And so what some people often do is take logarithmically big bins. And so they actually don't take, because we've been taking bins that have a uniform width, but in a histogram, you don't actually need to do that. So you can take huge bins for these down here. So there's probably some way of doing that in Julia, but I don't actually know how you do it.
You could, you instead of saying n bins, you can actually give intervals.
Yeah, but I don't really want to do it by hand.
No, it's messy, but it's doable. Yeah.
Okay. Anyway,
run out of time.
The end of the lesson, the class. So yeah, what do we see? So we've been talking about continuous random variables. So random variables which have a continuous range of possible outputs or outcomes. And so then we have to talk about probability density function, which is this slightly difficult concept where we have probability 0 to have any particular value, but we do know what the probability of being in some little region is. And that's given by this probability density function. And we saw how we can talk about non-uniform distributions and how to generate them. Anything to add? Well,
Okay.
great. Okay.
All right. So we'll end class now, I guess, and do differential equations on Monday, I guess.
yeah.
Okay.
Thanks, everybody.
All right. Take care, everybody.